Hey, good morning, everybody. Thanks for joining us. I know it's 9 o'clock. I don't know about you, but I haven't had my coffee yet. This is Pushing Packets. How do the ML2 drivers stack up? My name's James Denton. I'm a network architect, longtime OpenStack operator, and OpenStack Ansible contributor.
My name's Jonathan O'Malley. I work with Rackspace Private Cloud. I'm also a network architect.
Great. So one of the things we want to talk about today is we want to introduce the viewer to a few of the most common ML2 drivers available with OpenStack Neutron, kind of compare some of the virtual switching technologies behind those drivers, talk about some of the advantages and disadvantages as to why you would or wouldn't use one of those, and maybe help you determine what could be a good fit for your cloud. So we'll talk about briefly what ML2 is, discuss some of the most common mech drivers, provide comparisons, and we'll kind of summarize it up at the end. So in the beginning of Neutron, there was the monolithic plugin. Using a monolithic plugin, operators were limited to a single virtual switching technology like OVS or LinuxBridge within a given cloud. There wasn't a lot of flexibility there. Writing new plugins was difficult and often resulted in a lot of duplication in code, a lot of duplication in efforts. Around Havana, ML2 plugin was introduced. ML2 plugin consisted of, by using ML2 plugin, operators were no longer limited to a single virtual switching technology. They were able to leverage multiple technologies simultaneously, maybe Open vSwitch and LinuxBridge on 2 different hosts, as well as drivers that could be responsible for configuring the physical network infrastructure. With this modular approach, developers could focus on developing the drivers and not having to re-implement a lot of core facets of the Neutron API. 2 major components of the ML2 driver: type drivers and mechanism drivers. So type drivers describe the type of network and its attributes. For a VXLAN network, that might include VNI and VTEP information. For a VLAN network, that could be provider interface information, 802.1q VLAN information, and so on. The mechanism drivers are the ones responsible for actually implementing this logical network. So LinuxBridge driver implements the network using Linux bridges, OVS with Open vSwitch bridges. SR-IOV uses virtual functions, and so on and so forth. We'll cover just a few of those today.
So the goal here today was to put these mechanism drivers under similar tests to see how they perform. As James mentioned, there were a number of mechanism drivers we had to choose from. We chose the base 4 that you see here. We chose LinuxBridge, Open vSwitch, SR-IOV, and VPP, and then a couple derivatives of a couple of those. Again, the goal here wasn't to describe how to implement these or how to configure them. The presentation doesn't really lend itself to that. It's more of how they performed during our tests.
Cool. So our test environment consisted of a dual-node OpenStack Ansible-based infra and compute node running on a dual-socket 12-core Intel V3 processor. We utilized Mellanox NICs, including the ConnectX-4 and ConnectX-5. We enabled jumbo frames, disabled port security and security groups on all ports. We running parity there because not all mechanism drivers support port security. So we didn't want one to have an advantage over another if we could avoid it. The VM under test was an 8-core VM with 16 gigs of RAM running Ubuntu 18.04 and the latest kernel. We stuck to 8 cores and 16 gigs of RAM because our test machines were fairly limited in their capacity, but also we wanted to ensure that the VM itself could fit within a given NUMA node once we moved on to the DPDK tests. The mechanism driver table you see there in purple outlines which network drivers in the VM were active when we tested a given mech driver. So for the SR-IOV test and the ASAP² test, those utilized a Mellanox driver included with the Linux kernel. Everything else used a vHostNet driver.
We also wanted to mention that not all mechanism drivers support all type drivers. So for this test, we chose to use a flat network. So type flat for everything, again, trying to take the type out of the equation and focus just on the mechanism.
So a good question. So we are talking about a data plane throughput test.
Correct.
Yes. Yes, that's right.
Correct.
Yeah.
All right, so the first mechanism driver that we've chosen to test is the old standard LinuxBridge. LinuxBridge driver implements a bridge per Neutron network, and its goal is to provide instances layer 2 connectivity to the physical network infrastructure. For every network that we have in Neutron, we will have a BRQ bridge, a Linux bridge, on that compute if needed. So the requirements for the LinuxBridge driver are pretty mere. We simply need a physical interface of some type, be it a bond or a physical NIC, to put inside of a bridge. And then if you want to utilize any type of overlay technology or overlay networking, you need an IP address on that server. The agent running here is the Neutron LinuxBridge agent, and it's responsible for creating and programming these bridges to provide, again, instance connectivity to the physical network. And so here are the results. On the left, you're going to see a very high-level diagram of what we set up, and on the right, the realized throughput of our test. So on the left, we have an instance with 4 NICs. Each of those 4 NICs connects to a different Linux bridge. Each of those has a physical interface of an increased speed, so 10, 25, 40, and 100 gigabits per second NIC. The green line in the graph represents the results we got from a bare metal test. So pushing the same type of traffic through just 2 physical servers. The blue line represents what we got from our LinuxBridge test. At 10 gig, we were right up there. So we saw 9.3 gigabits per second. On the 25 gig NIC, we saw an increase in performance up to 18.7 gigabits per second. And then we saw a pretty severe taper. So on the 40 gig NIC, we were just over 20 gigabits per second. And on the 100 gig NIC, we were at 22 gigabits per second. Again, this is just our test.
And this is large frames?
This is jumbo frames, yes.
Jumbo frames enabled, iPerf, 4 threads. So
I believe it was a 120-second test.
right, duration of 120 seconds. So.
Do you need that little multi-queue?
No, so actually, one thing we wanted to kind of outline was, given the amount of tuning that's going to be necessary to really maximize performance for any individual test, we kind of wanted to just demonstrate what an out-of-the-box experience might look like for your run-of-the-mill operator deploying this and kind of what they might expect. So later on, we'll kind of cover some of the things you're mentioning there, tuning that might be required to get better performance.
But we try to stay clear of any high-level tuning just to show what it would look like for a standard user.
Yeah. Cool. So why somebody might choose a LinuxBridge driver over something else? It does support overlay networking, including VXLAN, which is probably the most popular technology for OpenStack. It's easy to troubleshoot using well-known tools available in the host operating system. It does support high availability routers, those that use VRRP, but it does not support distributed virtual routers, which requires Open vSwitch. You can configure bonds with the Linux bonding module. And it is widely used, documented, and supported. Some of the reasons why you may not want to use it is IP tables, despite port security being disabled, may still be in path. So there could be a performance penalty there. It does not support advanced services such as tap as a service, firewall as a service, and some others. And sometimes it lags in new features compared to the Open vSwitch driver, and for good reason. That has a lot more capabilities than a standard LinuxBridge environment would.
So the second one we tested was regular old Open vSwitch. Again, Open vSwitch is an open source virtual switch that connects virtual networks to your physical network infrastructure. It uses OpenFlow to program flows on these bridges. In a standard deployment, you'll see at least 3 Open vSwitch bridges, BRint, which is kind of the hub of everything. Unlike LinuxBridge, all your VMs, regardless of what network they're in, are going to plug into this integration bridge. From there, you'll see 2 branches, quite often a tunnel bridge, which is going to handle your overlay traffic, and then 1 or more provider bridges. And in our case, we're going to have 4, 1 for each speed. And that's where your physical interface and your physical network will connect. So So here are the requirements. They're going to be very, very similar to that of LinuxBridge. Again, you need a physical NIC. You need an IP address if you want to do any type of overlay network. And then you're going to need a couple additional packages, which may be included in your installation. So if you're using OSA, it will help you install that. If you're doing it by hand, you may have to install some packages on your own. As mentioned before, the same instance. This time we plugged it into an OVS bridge. So the 4 NICs all plug into the same integration bridge. 4 branches off of that, each with a different speed physical NIC. And the results, very, very similar to that of LinuxBridge. Yes, sir?
One question. Did you test the OpenVSwitch firewall driver?
We tested this with the firewall driver, the OpenVSwitch firewall driver. We also tested with LinuxBridge, with the hybrid. And the results were so similar, we chose to combine them to one. They were maybe a couple hundred meg difference, if that. No, joking. Very, very similar.
Yeah, and our test showed we found some things that were very interesting and would require and warrant further investigation. But in this case, I think I did mention we disabled port security, so I don't know if the firewall was actually in play for the OVS test.
But we did do both, and results were.
You still have the bridge, and there's one rule, one chain that gets hit. It's just an accept.
But it's there.
It's there. So.
How many flows were you pushing?
So given this was iPerf, I don't really know. It's probably elephant flows, but we do have some T-Rex tests that are a little interesting. But if we can take questions maybe towards the end, we have a lot of slides to cover, and I do want to answer all the questions we can.
Yeah. The point here was the results we got were very, very similar to that of a LinuxBridge test. At 10 gig, we saw basically 10 gig. At 25 gigabits per second, we saw an increase to 18. And then that same taper, where it levels off at 40 gigabits per second, we saw 20. And at 100 gigabits per second, we saw 22.
So with the Open vSwitch MEC driver and Open vSwitch virtual switches, we still get overlay networking. We get some VXLAN and GRE, but you also get Geneve if you decide to leverage the OVN mechanism driver down the road. You get all of the routing functionality provided by Neutron, including distributed virtual routing, which provides better east-west traffic distribution and a smaller failure domain. You get what is probably a more efficient OpenFlow-based firewall versus using IP tables hybrid. You get to leverage most of the advanced services like tap as a service, file as a service, and so on. You can still support bonding and link aggregation using the built-in kernel module or the Open vSwitch command set itself. And like LinuxBridge, it's also widely used, documented, and supported, and you can hit IRC and somebody there will be able to answer your question. Some of the disadvantages, traffic clearly isn't as accelerated as it could be because you're hitting both the kernel and user space data path. There's some context switching there that can have some result in some performance degradation. The command set, if you're not familiar with it, is a little tricky. And some of the interfaces used by Open vSwitch aren't necessarily exposed to, aren't available through standard tools. So patch interfaces, bridges, you can't perform packet captures on bridges, but you can create mirror ports and perform captures on those. So next, we went ahead and we implemented Open vSwitch with a DPDK accelerated data plane. So just at a high level, with traditional network drivers, getting packets off the wire is interrupt driven. When traffic is received by the NIC, an interrupt is generated and the CPU stops what it's doing to grab the data and perform further processing. The more traffic, the more interrupts, resulting in less performance. DPDK uses the concept of pull mode drivers versus interrupts, which means that one or more cores are constantly polling the queue rather than relying on CPU interrupts for traffic processing. In the case of OpenStack Neutron and Open vSwitch is the application that is leveraging DPDK. There's nothing that a user needs to do within their VM to leverage that technology. Some of the requirements here, just like the others, right? We need some physical interfaces. We need an IP address for offloading. I'm sorry, as a VTEP. But your NIC has to be supported by DPDK, which means now you need to reference the hardware compatibility list at dpdk.org to make sure that your NIC is compatible. You get to play sometimes a driver dance. We found with Mellanox things could be a little tricky there. And now you have to worry about huge page allocation reservations and the NUMA topology of the node you're deploying on. Right, so here our setup looks a lot like a standard OVS. We still use the same integration bridge. We still have the 4 provider interfaces. And we saw that performance with DPDK was improved over vanilla OVS. Maybe not as much as we expected, but I think a lot of this has to do with our lack of tuning and maybe our lack of NUMA awareness in this particular setup. I would have expected a little bit more near the green line there, but we definitely did see some improvement. Two, yes. So the advantages. We get to leverage all the cool stuff that we got to use with Open vSwitch. And we do get better performance because we are using the DPDK framework. Now, some of the disadvantages may be that non-instance ports are not supported. So things like TEP interfaces that may be connected to network namespaces, leveraged by firewalls as a service, LBAS, and DVR. You do have to worry about huge page configurations, which means now you are configuring kernel parameters in Grub, maybe using a DPDK service to set up those huge page reservations at boot. And you're also having to modify flavors in Nova to make sure that instances get spun up to leverage huge pages. Your NUMA topology is going to play a big part in this as well because some of your resources are split across CPUs, so you want to make sure that you are leveraging maybe 2 NICs, 1 in each NUMA node. Your memory gets split between the 2 NUMA nodes, which may restrict the amount you can associate with a single instance. Otherwise, you might split the nodes and kind of get worse performance.
Which we very well might have happened in our tests.
Yeah, we tried to avoid it, but again, we didn't go into too much effort to avoid that. Great, so next we took a look at SR-IOV. So OpenStack Neutron provides an SR-IOV NIC switch mechanism driver. That's not anything that you have to install. That's kind of included in the base package. With SR-IOV, we get to split a PCI device into a single PNIC and multiple VNICs. And each of those VNICs can be associated with a single Neutron port. As this little diagram shows, by leveraging virtual functions, each instance gets to bypass the hypervisor in the kernel and really has direct access to the traffic and the memory there.
So the results. Pretty close to what we had with our control bare metal test. I don't really need to go over the numbers because we basically get line rate. We got, I think, 70.3 at the most of the 100 gig NIC on our bare metal test, and we were right there at 69.8 with SR-IOV. On the left, you're going to see, again, the high-level setup. Same instance, same NICs. This time, each NIC has a dedicated virtual function. That virtual function connects to a physical function, which again goes down to the physical networking infrastructure.
So some of the advantages. Near line rate performance, right, is pretty clear there. Traffic does not traverse the kernel in this case, so we get to bypass a lot of the overhead there. Now, the list of disadvantages is somewhat large, but there's some good news there. So right now, live migration is not supported when you're using SR-IOV direct mode. However, there appears to be some work done, especially in the train cycle, to help alleviate that. Interfaces, the virtual functions are not really accessible to tools on the compute node. We'll talk about indirect mode in a bit that kind of helps alleviate that a little bit. It only supports instance ports. So again, all of the other sort of L3 related ports for DVR and routers and LBAS and whatever, those all will leverage another technology like LinuxBridge or Open vSwitch. And you can use SR-IOV and any of those others in parallel as long as the NIC used for SR-IOV is probably not used for something else. Bonding and lag is not currently supported, although there is some work being done to ensure that an instance can have two virtual functions that are split across two physical functions, and you can perform bonding in the VM. Port security and security groups are not supported. Interface hot plugging is not supported. And one of the big things is a change in user workflow. So a lot of users, I think, are very used to leveraging the OpenStack SDK, CLI commands to just perform a Nova boot command or an OpenStack server create, specify a network, and go. In order to leverage SR-IOV, you have to set a VNIC type on a port beforehand and then specify that port as part of the server create. So if you have automation in place that helps create your instances, it's not a big deal. But as people that use, say, the Horizon or CLI tools, it might be a little bit of a change. So next, we're going to take a look at SR-IOV indirect mode. And indirect mode uses an intermediary device, such as a Mac VTAP interface, to provide connectivity to the instances. So rather than attaching the virtual function directly to the instance, the virtual function is first attached to a Mac VTAP interface, which is then attached to the instance. So this particular architecture addressed some of the shortcomings of direct mode, especially related to live migration. But we'll see in the next slide that the performance benefit once you get over 10 gigabit is effectively lost. So here on the left, we have just a modification of that last diagram. But instead of the VM being connected directly to the virtual function, now we have this Mac VTAP interface there. The great thing is that Mac VTAP interface is exposed to the OS. We can perform TCP dumps on it. We can use all sorts of tools to get metrics on it. The bad thing is, once we exceed 10 gigabits per second, we really start to see things level off and really hit a max of about 20 on a 40 gig NIC. I don't know what we could have done necessarily to help make that more efficient. And it's very possible that at the time this mode was introduced, 10 gig was sort of on the bleeding edge, right? Now we're looking at 100 and beyond. And this technology may not be a good fit for most workloads these days. The big advantage of SR-IOV indirect mode over direct mode would be that you do get live migration. You do get the visibility on the underlying OS. And there's no additional setup beyond the initial SR-IOV configuration, other than your workflow does change here as well. But instead of specifying direct on the port create, now you're specifying Mac VTAP. The SR-IOV NIC agent handles all of the plumbing for you. Disadvantages above 10 gig, we saw that drop off in performance. Again, the workflow piece. And so really, a lot of the performance benefits we saw with the SR-IOV direct mode are really lost over 10 gig. All right. So moving on, we took a look at Open vSwitch with hardware offloading. And hardware offloading is a topic I've seen talked about a lot here at the summit. And what that is it is a solution where the NIC itself has a switch built into it. And a lot of Open vSwitch flows can be offloaded to the NIC. For us, we were using Mellanox ConnectX-4 and ConnectX-5 NICs. Mellanox's implementation of hardware offloading is called ASAP². They leverage the SwitchDev API. And Open vSwitch is compatible with it, and OpenStack is good to go. You still leverage the standard Open vSwitch mechanism driver and the Open vSwitch agent. Everything from a user configuration standpoint looks relatively the same. But now you're leveraging SR-IOV in addition to Open vSwitch. So with ASAP², that concept of the E-switch in the NIC and a VF representer port are introduced. So a representer port is a virtual representation of an E-switch port. These ports are created and associated with the virtual function and attached to the OVS integration bridge. The instance itself is attached to the virtual function and requires drivers for the virtual function, just like SR-IOV did. When you send traffic to the representer port, it arrives on the virtual function and then to the VM. And if the VF receives a packet from the VM that the E-switch doesn't have a rule for, the packet hits a slow path and traverses the standard OVS data path, and then subsequent packets hit the fast path through the NIC. And we can see here the results look awfully similar to that of SR-IOV. Near line rate performance, very comparable to our bare metal test. Very impressive, leveraging both Open vSwitch and SR-IOV technologies. The advantages over SR-IOV especially is now we can support link aggregation and bonding at the vSwitch level We don't have to worry about implementing those at the VM if we don't want to. We are limited to leveraging ports on the same NIC. We cannot build a lag between 2 different NICs on the same host. But we do get that level of redundancy between the ports and definitely at the switch, physical switch level. We get the mirror traffic using the standard OVS command set, so port mirroring, TCP dump. And the majority of packet processing is done in hardware. Once that first packet hits the slow path, then the flow is pushed down from vSwitch to the NIC. One of the disadvantages of our particular implementation with ASAP squared is that sometimes the Mellanox drivers in this technology aren't officially supported on non-RHEL-based OSs. So in our test, we used Ubuntu 18.04. Didn't really have a problem, but it may be difficult to get support in the community if you're not using a RHEL-based OS. The use of security groups and port security means that packet processing is not offloaded at all. That's something that we found once we enabled the OVS firewall driver, hardware offloading stopped, right? Now, there is some work being done and may already be released in the latest driver where those flows too will be offloaded to the NIC, so we can expect better performance. That's a good question. Can we circle back on that maybe afterwards? I have to think about that one. And maybe we can re-ask because I only got part of it. Lastly, we took a look at VPP, which is another virtual switching technology, sort of contributed by Cisco. The marketing materials say it's a very fast packet processing engine, and I'm likely to believe them. We don't have much experience with it in production. We thought we'd throw it in here and kind of see what it did. So networking VPP is the GitHub project where they maintain the mechanism driver that you can install to implement this in your cloud. So in this vSwitch, when you use the utilities, you might notice that some of these provider mappings look kind of weird. My 10G provider label maps to an interface named 25 gigabit Ethernet 400. That very much looks like a physical switch in the way in which it named the interfaces. So you can see that that technology sort of made its way into the vSwitch here. OK, with VPP, we found an instance with 4 interfaces, all connected to the VPP vSwitch. All 4 physical interfaces also connected to that vSwitch. 10 gig and 25 gigabit performance, we hit line rate. But once we tested on the 40 and 100 gig NICs, we saw an actual drop in performance there, which we can't really explain.
We need to look into that.
VPP uses DPDK for its acceleration, so it's very possible that we were naughty and didn't plan our NUMA topology correctly. But that's something that we would want to look at, maybe work with the VPP, networking VPP community to really vet out. So an advantage of that is that it was definitely accelerated over LinuxBridge and vanilla OVS, even maybe OVS+DPDK. Over 40 gigabit, we definitely saw that drop. This driver may still be considered experimental for the greater community. I know it is used in production, and I'm sure people are very pleased with its performance. We need to get more information on it and really determine the best way in which to configure it. Because we were using Mellanox NICs and the Mellanox drivers not included in the DPDK binary, we actually had to recompile DPDK with the Mellanox support and then recompile VPP with the recompiled DPDK libraries to get it to work. We don't know if advanced services are supported because we don't know how they interface and plug into that VPP vSwitch. We don't think that you can run the VPP vSwitch in parallel with other MEC drivers on the same node, but you can definitely run them in parallel in the same cloud. And again, the driver dance between OFED, DPDK, and OVS is a bit tricky and not necessarily something I want to maintain long term.
All right, so what we've all been waiting for. We've shown you the speeds and the throughputs that we've gotten from all our tests. Thank you. But now we wanted to kind of bring them all together to show you them side by side. So at 10 gig, they all kind of shot par right there at 10 gigabits per second, no surprise, no major difference. At our 25 gigabit per test, we saw LinuxBridge, OVS, and SR-IOV indirect or MAC VTEP take a little bit of a hit. DPDK, SR-IOV, ASAP squared, and VPP maintained very, very close to line speed. At 40 gig, here's where we saw the dip in DPDK, as well as VPP. LinuxBridge OVS MAC VTEP, again, right about that 20 to 22 gigabit per second mark. SR-IOV and ASAP are still the outliers. And finally, 100 gig test. Everything fell below 50% of line speed, except for SR-IOV direct and ASAP squared. Again, these are our tests. These are our results from just one of many tests that we could have run, but these are the results that, and the data that we got. Throughput was not the only thing we wanted to test. It was our primary concern for our metric, but not the only thing. We also wanted to test other factors of performance as well, which is...
Yeah, so I mean, iPerf is a very common test, but it's probably not the most, definitely not the most thorough test one could do. If we had the time, we would have tested netperf, we would have tested latency, jitter, all those kinds of things that are important to a lot of people. I don't have a degree in T-Rex. I've used it a few times. It's somewhat difficult to set up. It does use DPDK, and it is a great tool. Our goal here was really just, given our lack of time, we just wanted to push as much traffic as we could through the device under test, connected to different vSwitches, and see which one fell down first. So in the first test, we leveraged one of the SFR profiles provided by T-Rex. It uses profiles consisted of TCP and UDP traffic, including HTTP, DNS, SIP, SMTP, Exchange, and a few others. Varying byte sizes, varying protocols. That test is meant to replicate 1 gig of sustained traffic, so we multiplied it by 10. We ran it for 120 seconds, and this is what we found. So we found over that 120-second duration, T-Rex was opening roughly 40,000 connections per second, pumping roughly 2 million packets per second. All but SR-IOV, ASAP, and the bare metal test really kind of fell on their face. LinuxBridge and OVS and MAC VTEP technologies, there was significant packet loss there. With DPDK and VPP, we hit anywhere from 24 to 40% packet loss. Bare metal to SR-IOV, less than 1%. At 25 gig, we started to see a little bit more packet loss on the ASAP and SR-IOV vSwitches. Bare metal, again, was right around 0%. And the SFR profile, was multiplied by 25 times, initiating 100,000 connections per second and roughly 5 million packets per second. At 40 gig, now we were opening 160,000 connections per second and 8 million packets per second. We can still see SR-IOV and ASAP squared hanging in there. That's not an environment I would really want to be using at that moment, but at least it's better than some of the others. And lastly, 100 gig. Everyone's in the yellow, some in the red. 20 million packets per second, 400,000 connections per second. What we were seeing here is T-Rex itself was starting to get some buffer full errors. We know that the device under test we were monitoring CPU utilization. We weren't CPU bound. So was it VirtIO? Was it the vSwitch technology? We don't really know. Again, with more time, I think we would want to really dig down and figure out where we could optimize this stuff. And in our summary, we'll talk about some of that.
So speaking of summary, everything we've talked about today thus far has been a quantifiable metric. It's been a speed, but we also want to talk about the non-tangible things. We want to talk about things like how difficult it was to install and maintain. James had to recompile drivers on a couple of these examples, which I would have wanted to. We want to talk about things like upstream support, bug submission rate, bug fix rate, how much has the community adopted it, which features it had, which features it didn't have, and then, of course, hardware compatibility, and then overall ease of support. And this is kind of the scope that we came up with. LinuxBridge, by far, we thought was the easiest, just to maintain, support, install. Open vSwitch was the next. SR-IOV following that. Again, this is a completely subjective example, right? There's no way we can quantify this, just our opinions. SR-IOV was right about in the middle. and then it started getting more difficult with ASAP, Open vSwitch with DPDK, and lastly VPP.
Yeah, so as the results show, I think a significant amount of tuning would be involved to get a better performance out of some of these technologies, but it's definitely possible. In that case, it may warrant working with the vendor of your particular NIC. I know Mellanox, if we reached out to them, they would have helped us with some of the kernel level tuning that we could have implemented on both the device under test and the host performing, the compute node itself. Each vSwitch probably requires its own tweaks. Every workload is going to require some different tweak, whether it's different allocation of huge pages or more RAM, more PMDs. For LinuxBridge and OVS, I have here, you can't squeeze water from a stone, right? Some of those are just kind of limited, which is why there are enhancements and accelerators for those technologies. The hardware you're using definitely makes a difference, right? So you're definitely going to get better performance even with SR-IOV when you're using something like an XL710 versus an old X540. ConnectX-5 is going to be better than the ConnectX-3, even at 40 gig, right? The hardware you're running, the compute node specs, whether it's CPU speed, the PCI bus generation, right? We couldn't hit line rate on a 100 gig NIC because we're running PCI 3.0. With 4.0, now we can start to exceed 100 and 200 gigs. And here, there's a tendency to want to run some of the latest technology. As a new operator kind of coming in, there's a lot of options here. When you see acceleration, I want that. I want to go fast, right? But there's a lot of overhead involved with implementing that and maintaining that technology. So once I start looking at having to maintain DPDK on my own, or VPP, and recompiling those after every upgrade, or making sure my users are properly leveraging flavors and NUMA resources. It's a lot of work. And given the results that we had, if we were just going strictly based on that, we might look at the two of those and say, well, why am I looking at DPDK and not SR-IOV? Right?
Encourage you guys to consider what features you may need, what features you don't, compared to what speeds you're looking for, and really think, is the juice worth the squeeze?
There you go.
I think is the phrase. So the summary, down to brass tacks. Best performance, these were not a surprise. SR-IOV direct mode and Open vSwitch with ASAP squared. Those offered us the best performance on pretty much all of our tests. For best support, meaning easiest, as well as perhaps most widely used, LinuxBridge and OVS, tried and true.
Yeah. So we will share the slides. I'm happy to post them up on Twitter, and some of the resources that we leveraged here is just a few of the links. I mean, there's a lot of information out there. The community's great, though. If you are on IRC, hit me up. OpenStack Neutron's a great place to ask questions, and there's a lot of operators in OpenStack Ansible too that can really kind of help you focus on and make a good decision. So that's it. Thank you. So if there's any questions, feel free to come to the mic. We'll do our best to answer them in the few minutes that we have left.
So just a tip, having run SR-IOV at production scale and very large environments since before OpenStack supported it, just native KVM. If you're still thinking of your compute nodes as a box of sockets and cores and RAM, stop that. Just stop. Think of them as NUMA nodes. Think of it as sockets, and figure out which PCI slots and which RAM banks tie to those NUMA nodes, and draw them as such. Include your PCI slots, and then your VFs attached to dotted decimal PCI slots on each of those, regardless of what you choose. But for SR-IOV, it's mandatory. So as you guys mentioned accurately many times, the NUMA is everything, huge pages at 1 gig, right behind.
Well, that's a great point, right? Because we kind of take for granted that the scheduler is actually helping us make that decision for us, so it's a little abstracted, right? SR-IOV especially, it is actually selecting the NUMA nodes and cores associated with that NIC. But as a user, I'm not seeing any of that, right? But I definitely take it into consideration with the DPDK stuff.
You can absolutely sabotage the scheduler filters by not doing the low-level mechanism driver configs correctly and not setting up your providers correctly. So you can feed Nova scheduler garbage or just let it guess.
Yeah.
So hopefully that helps folks.
Well, thank you very much.
Was all of your testing single VM on a compute? Did you do any testing where you were overloading a single
Unfortunately, no, right? So the question was it a single VM on a single compute? And yes, given the time, we didn't really have the time or the testing tools necessary to collect the data if we were able to get it. So there was some really nasty Ansible involved in this and collecting the data, especially for the iPerf tests, scraping tools that didn't have JSON output and stuff. Some of the hardware we only actually acquired 2 weeks ago, so it was really tight constraints, but definitely I would want to really blow up the compute node and really see where things start to fall off from a compute resource standpoint. Yeah.
Especially for those technologies that are using kernel space.
Absolutely. Yeah. One thing we did notice is the tests that we were doing weren't enough to really get the CPU up anywhere, so we don't really know where that bottleneck was. So, great. Well, thank you, everyone. Have a great rest of the summit.